here. And I think I found p squared before, but I didn't write it down again. So I'll just do it quick on the board. So this should, technically should already be, it's on video somewhere. I'm finding p squared, but let's go ahead and do it quick. It's always good to see matrix multiplication. So I'm taking p times itself. So I'll take the first row times the first column. I have 9/16. 3/4 times 3/4 gives 9/16 plus 1/12. So what, 9/16 plus 1/12. 3/4 times 1/4 is 3/16 plus the 1/4 times 2/3. So what's this? 3/16 plus, really that's 1/6. 1/4 times 2/3 should be that. Okay, and then let's see, 1/3 times 3/4 is 1/4 plus 1/3 times 2/3, which is 2/9. And then let's see, that's 1/12 plus 4/9. Okay, so you guys can double check the math here, and you simplify these fractions. I don't think I'm going to do it here on the board just because I'm just trying to illustrate a point. I don't want to get bogged down in adding up fractions in the moment. So these are some numbers. Again, I just took this matrix and multiplied it by itself. I get this matrix. So now the answer to our question is take this row vector and multiply it by this matrix here, this p squared. So we'll do that. And then that should be able to tell us the answer. So x2 is x0 times p squared. X0 times p squared is this row vector times this matrix. The answer will be another row vector. And what it will be, well, so I have to take this row times the columns of this guy. So I'm going to take 1 times this plus 0 times this. Well, that's just this entry. So it's going to be whatever 9/16 plus 1/12 is. And for the second guy, it's going to be, again, 1 times this entry, and then 0 times this entry added together. So that's just 1 times this entry. It's just this entry. So that looks like 3/16 plus 1/6. Okay. And so now I have the state vector after 2 days. This is 2 days later. Or this is our state vector. These represent the probabilities of it being sunny or rainy 2 days from now. So we have both. And what we were interested in is the probability of rain, and it is this. And if memory serves correct, that matches, maybe after I simplify the fractions, that should match our answer that we got before. In fact, I think this is 17/48, which is what we got before, if memory serves correct, in this weather example. So maybe go back and check our old work to make sure. But anyway, this is our answer. Okay, so we've sort of resolved the problem that we have done before, but now we've sort of altered the language. I'm talking about state vectors and stuff. So really, nothing we did here is any different than what I technically did before, but I've just sort of recast it using this language of state vectors, which will end up being useful for us in a moment. So let me pause here and ask if there are any questions. Okay, it doesn't sound like it. Cool. Let's do another example just because we should get comfortable using this language of state vectors and probability vectors. Let me do another example. This one will be more abstract in the sense that we won't have a weather example. I'm just going to say, suppose we have the following Markov chain. Suppose we have a Markov chain, and the transition matrix is E equals 0.3, 0.7, just 1, and then 0. So let's say I have a Markov chain with this transition matrix. And here's our goal. Let's just find the state vector after 2 transitions. Given the initial vector and we'll call that x0 equals 0.6, 0.4. So again, I have to have a starting point. So I need an initial vector, initial state vector. It'll be this x0 equals 0.6, 0.4. That's our initial probability vector here. Given that, what is the state vector after 2 transitions? That's what we're looking for. So I'm basically doing the last problem again, but with different numbers is basically all that's happening here. Because we're still looking for after 2 transitions, say. Okay. And so again, I want to highlight the fact that I need a starting point. You know, if I don't give you an initial vector, this question of finding a state vector after 2 transitions no longer makes any sense because it matters how things begin, you know, where I start from. So that's worth pointing out. And it's also worth pointing out that here, there's no certainty in which state I'm starting in initially because these are probabilities and neither of them is 1, neither of them is 0. But like there's like a 60% chance of being in state 1 and a 40% chance of being in state 2. But we don't actually know which one you might start in, right? So there's some ambiguity here, but that's okay. In the end, all we're going to do is a mathematical computation, so really that won't matter. But sort of intuitively thinking about it, it's good to notice that. You know. In the last example, we knew for sure we were starting in sunny. In this case, it's like if this was still sun and rain, there's only a 60% chance of sun today and a 40% chance of rain today. How does that affect the chance of rain, say, 2 days from now? That's what we'd be answering here. Okay, so enough of that. Let's go ahead and just do the problem. So again, all I really need to do is note that x2, the state vector after 2 transitions, can be found by multiplying my initial vector, x0, with the square of the transition matrix, p squared. So I need to do this computation. So first, what I would need to do is find p squared. So we'll find p squared. So again, I'm multiplying a matrix by itself. So I would take first row times first column is 0.3 times 0.3 plus 0.7. So that's 0.09 plus 0.7. So that's 0.79. And then we're taking first row times second column. 0.3 times 0.7 is 0.21. Plus 0 is just 0.21. And we double check to make sure these do in fact add up to 1. So we're good because this is a transition matrix, so the rows have to add up to 1. So far it looks good. Now we do the second row. So I'm going to take the second row times the columns. So that'll be 1 times 0.3 plus 0, so that's 0.3. And then 1 times 0.7 plus 0, that's 0.7. And again, this adds up to 1. So it looks like we're okay. So this is my matrix p squared. So now I'm going to take this x0 times p squared, and that'll be my x2. So x2 is x0 times p squared. It'll be another row vector with 2 entries. And I get it by multiplying this row vector on the left with this matrix on the right. So I'm going to take this row times the columns of this guy. So what's 0.6 times 0.79 plus 0.4 times 0.3? Well, I'll admit I'm not doing this part in my head. I have it written down. If you do that computation, you should get 0.594. And just multiply the 0.6 and the 0.79 and add it to 0.4 times 0.3. And then for the second one, I'm going to take 0.6 times 0.21 and add it to 0.4 times 0.7. And that'll give me 0.406 if you check the work. So here is my answer. I mean, all we're asking for here is the state vector itself. And so here we have succeeded. Here is my state vector. 0.594 and 0.406. You can check these do add up to 1. And so these represent the probabilities of being in state 1 or state 2 after 2 steps, given that this was my initial state vector. Okay. So as always, the state vector after k steps depends on the state vector initially, the initial state vector. It all depends on where we start. Okay. Okay, so are there any questions here? Let me check time. Okay. Still have plenty of time. Okay, so what I want to start working towards now is the namesake of this section, which is the regular Markov chains, and what those are about. And so, you know, I've been hammering this point about everything depending on your initial state vector. And so that's true. And so you might ask a question of like, how much do things depend on the initial state vector? You know, if I pick completely different numbers for this initial state vector, how much would that change this answer? Yeah. So how much do the results after k many steps depend on the initial state vector? And even more so, we might extend this, you know, we've just been doing with like 2 steps. You might do this with like 3 steps or something, right? 4 steps. Those are reasonable computations that I could ask you to do. But in the real world, you might care way more about long-term forecasting and stuff, right? You might want to be able to make predictions about the state probabilities like 1,000 steps, you know. If you're a farmer and you care about the weather because you have to plant your crop, you might want to be able to use our, you know, say you're using our basic weather example, which I kind of just made up, so it doesn't apply to reality at all. But say it did. You have some Markov chain representing the weather, and you're a farmer. You want to make predictions about the weather throughout the year or throughout future years, because you want to know when you should plant your crops and how much water they need on a given day and all that stuff. So you need to know about when it's going to be sunny and when it's going to be rainy and so forth. And so you'd like to make those predictions. And so you would like to see over a long period of time how this system behaves, how the probabilities of the states of the Markov chain vary over time, over a long period of time. And so it stands to reason that maybe sometimes, if we're lucky, nice, stable things are going to happen. Like things are going to tend towards one state. Like maybe over a long period of time, it's mostly going to be sunny. Most of the time it'll be sunny. Occasionally we'll get rain. Maybe it'll mostly be sunny. This is a bad example because weather doesn't work this way, but hopefully you see my point is that we want to sort of look at the long-term nature of these Markov chains, how they behave over very long periods of time. Can we make any predictions with certainty over a long period of time, or are things just kind of random and chaotic? Well, we don't want to deal with random chaos because that's hard to deal with. There's an entire theory of math about chaos that I can't get into. And so instead, we're going to focus on regular Markov chains, which are the ones where there is some stability. There will be stability. We'll be able to make, in theory, some long-term predictions with regular Markov chains. This regular Markovs doesn't make any sense. Markov chains. So these are the guys we're going to focus on now because they're going to be nice. They're going to let us make long-term predictions. Okay, which is what we'd really like to be able to do if we can. So now, after having told you that, that's our motivation for where this is coming from, let me give you a definition that will appear to not relate to that at all, but I promise it will. So here's our definition, and this just is what a regular Markov chain is, mathematically speaking. So a Markov chain is regular if its transition matrix, P, satisfies the following thing, is such that, and then this following condition has to hold. There is a positive number, a positive integer. That's just a whole number, k, so that when I take the kth power of p, there are no entries that are 0. Every entry of this matrix, p to the kth power, will be a positive number. Has all positive number entries. So your Markov chain is regular if when I take the transition matrix, I can take a big enough power of it so that every entry is non-zero. Everything is not to 0. It's all positive numbers. This is a regular Markov chain. So again, it's not immediately obvious what this has to do with what I was just talking about a second ago. Like why should we call these regular? Why will these have stability so that I can make long-term predictions?